сделал. Участники, может быть, управление встречи, может, участники. Нет. Чат посмотреть. Ага. Посмотрим. Ссылочка есть, там гурта нет. Начинать тогда уже, как его, да. Все, да, есть. Hello, hello, dear colleagues, dear Dr. Laviraj, how are you? Can you hear me? Hello. Good afternoon. Can you hear me? Hello. Звука нету.
I think Professor Coleman, Professor Laviraj is having some technical glitch. He's just resolving
Now
that.
it is clear.
Okay,
great.
okay.
I can hear him.
Hello, Professor Corman. How are you doing?
We are fine. We are fine. Very happy to see you. So let's start. So, dear colleagues, dear friends, thank you so much for attending this online lecture. So we are happy to start the second mini lecture as pre-conference activity. As you well know, in November, we arrange our conference on multi-scale and multifunctional neuromorphic materials. So this is the second mini lecture. The first mini lecture was kindly provided by Professor Dr. Laviraj Gupta. It was amazing. So experience, all our students got impressed by the wonderful presentation. So today I would like to give a floor to Dr. Vladimir Smirnov, leading researcher of the research laboratory of neuroelectronics and neuromorphic nanomaterials. So please, Dr. Vladimir will tell us about neuromorphic materials for devices and systems.
Thank you, Dr. Corman. Dr. Laviraj, dear colleagues, dear friends, nice to meet you. My name is Vladimir Smirnov. I present you mini masterclass, which divided to first international conference on multi-scale and multifunctional neuromorphic materials. My topic of my speech, materials for neuromorphic devices and systems. Let me introduce where we're from. I present a scientific and research laboratory, Neiroelektronics and memristive nanomaterials, Southern Federal University, Institute of Nanotechnologies, Electronics and Equipment Engineering. This laboratory was created last year under financial support of government of Russian Federation and the mega grant project. Our lab include 33 participants, 3 full professors, doctors of sciences, 16 associate professors, 4 PhD students, and 10 master students. The area of research, neuromorphic devices, let me mix synapses and neurons, phenomenon of resistive switching in oxides, determination and control of functional nanomaterials characteristics, the development of electronic devices using memristive nanomaterials, oxides, 2D materials, and other. Our lab is include leading scientists from different countries, from South Korea, from Germany, from India. This is Dr. Laviraj, this is Dr. Chan Prakash, and leading scientists from Russia, from Nizhny Novgorod State University. This is Viktor Kazantsev and Alexei Mikhailov, and from leading scientists from Southern Federal Universities. Okay, let's start. I want to introduce some actual points of my speech of this area, what I present. The technological progress needs for high performance computing associated with unstructured data classification and pattern recognition. Increase in speed and memory capacity of ICs don't lead to significant increase in speed of data exchange between various nodes of computing system built on basis of one human architecture, the principle which the physical separation of processor and memory. A promising solution to solve this problem is a transition of computing system for the one human architecture to another perspective architecture close to the structure of the human brain, which is the set of parallel connected computing elements, this is neurons, and interconnectings via synapses, neuromorphic system. In this architecture of this kind, the processor and memory are integrated in a single device, and information processing steps are performed in parallel. Also, today, neuromorphic system can be integrated in ICs, extending the capabilities of CMOS technologies. Currently, there are several examples of physical implementation of neuromorphic system based on CMOS technologies. However, the processing and storage of information using digital to analog converters are associated with low accuracy, high power consumption, and many design problems. Therefore, there is a need to develop new element base of nanoelectronics, which would make it possible to implement the computational primitive of the human brain. On the way of the technical implementation of neuromorphic system is the crossbar topology based on memory star structures, and the advantages was which include a high degree of integration, the presence of analog parallel computing, and low power consumption. Physical implementation of artificial intelligent neuromorphic systems. There are several physical mechanisms such as conductive filaments formation, phase change memory, and using electronic effects. Memory star is in central part. We can see the different structures which use the different mechanisms, and therefore the structure use different memoristic nanomaterials. These materials used in producing different types of memory, like PC memory, phase chain memory, resistive switching, resistive random access memory, and ferroelectric memory. Also, memoristic structures and memoristic materials, this is a perspectives materials for creating and development different artificial neural networks, like present on this slide, artificial neural networks and spiking neural networks. Neuromorphic materials is a perspective materials for produce different neuromorphic systems which can be applied in robotic system creation, such as neuromorphic structures which produce visual perception, novel cognitive application, pattern and speech recognition, artificial creativity, predictive analysis, such as different types of memory, like maybe you take this control. Different types of machine vision systems. Here we see the different roadmap of realization, new paradigm of vision systems on conventional image sensor, electronic synapse-based visual systems. Here, memristor, crossbar arrays, synaptic device, and photo detector include in one common device, pre-processing and post-processing systems include in one device, and in the future we can see the one device image system and post-processing system include. The next application, this is a neuromorphic nociceptor memory systems, pain sensitivity, and neuromorphic tactical memory system, which can used in Android robotics for detecting the pain signals or tactical signals from hot and cold surface temperature, or soft and different physical parameters of surfaces. Neuromorphic motor memory system for memory of movement of hands of robots or prosthetics. Okay, after application, we speak about memoristic materials. There are many memoristic materials. This is a table of elements which use in produce different oxide, metal oxide elements which using in resistive switching phenomena. The other hand, we can use different 2D materials. Here we present classification and integration of 2D materials. This is a graphene family, 2D halcogenates, 2D oxides. What we say about 2D materials, here we present summary of 2D layered materials used for memoristic and neuromorphic application. There is in center 2D layered materials, memoristic devices, application for memoristic neuromorphic computing. In performance of memoristic devices is the power consumption, reliability, flexibility, integration. In neuromorphic computing, we interesting about artificial electronic synapses, artificial optoelectronic synapses, and from another part of slide, we can produce summary of memoristic devices based on 2D materials, which include lateral, vertical, and heterojunction structures, and schematic illustration of general mechanism in low resistance state and high resistance state. Two different devices, memoristic devices like lateral and vertical is very popular. Heterojunction structures is difficult to produce these structures and need more higher technologies. The next class of memristor, this is a flexible memoristic materials. We use a different active layer, memoristic layer, which grown on different flexible structures. Polyimide structures, flexible and transparent tantalum variable memristors. We use PET substrates for using in neuromorphic structures for robotic systems. The next promising materials class is biomaterials, which consist of green electronics, some present work in development of biomembranes present on this slide. We're using the ferritin, sericin, lingin, chitosan biomembranes, peptide, protein nanowires, and create the biorealistic application of memristive structure in producing of biosensors for different fields of application. When we produce different memristive structures, also we need methods to measure the resistive switching device. Here I present common structures for study this class of devices. Here we see SIM images of three main types. This is top electrodes deposited on blanket samples with common bottom electrode. On A. On B, we can see cross-point resistive device. And on C, we can see crossbar structure formed by multiple cross-point structures interconnected. There are some main electrical parameters which used in investigation of memristive structures. This is a resistance, and we use different tests for investigation. First test is an endurance test, which plot collected by three different methods. By measuring several current voltage characteristics curves and extracting the resistance at common voltage by using pulses, stress recordings the currents simultaneously and calculating the resistance from each cycles, and by using pulses stresses without measuring the current. The next test is measuring the retention and relaxation times of resistive switching device. We measure current time curves and by using common voltage of read operation typically is 0.1 volts, showing the retention of the low resistance state as it can be observed in strongly dependent on the current limitation. The next method to study resistive switching, this is a statistical analysis to evaluate the variability of resistive switching device. We measure current voltage sweeps showing the typical bipolar resistive switching during, for example, 100 cycles or 1000 cycles. And create after that different histograms, different different figures of cumulative probability and provide the statistical information. The next test of resistive switching, this is a switching time and energy consumption. On this slide, on the left figure, we can see schematic of the setup recommended to the characterization of switching time and energy. The bias is applied using the pulse generator and series resistors used to limit the current across the device in low resistance state. After that, we measure voltage and current signals with the oscilloscope and present on the figure the present the figure our time of resistive switching. The next methods of study resistive switching is nanoscale methods. This is a scanning probe, current microscopy, present on the left side of the slide. Schematic of a nano-sized memristive structure using the tip of the current IFM as a top electrode. On the B, we present typical current voltage curves collected with the standard IFMs tips, showing the resistive states. On C, we present block diagram on the connection of current IFM tip working in vacuum for nanoscale characterization. This very very good method to provide information, present information, visualize the information of resistive switching phenomena. On the right part of the slide, we present in situ TM characterization, TM images of high-resolution TM images of the switched structures and how the physical mechanism works in these materials, we can see by TM. The next method for study resistive switching device is the theoretical methods. We can use different simulation models for characterization of memristive materials, describing the provided information level and details. So we can use microscopic models, different models for characterize the macroscopic properties, atomistic dynamics, and we use compact models, this is phenomenological models, to simulate the physical processes of resistive switching. For creation of memristive materials, we use different technologies. One of the prospective technology, this is a printed electronic based on 2D materials inks. We create 2D material inks from 2D materials, from graphene, from halcogenides and other, and use the preparation properties and application of memristors. Here I present some schemes of producing the memristive materials by additive technologies. On the right part, we can see CMOS process steps for large-scale ICs, where we use photolithography technology. On B, a simple printing process for pure additive manufacture. We can use inkjet printing or 3D extrusion printing or other prospective technologies like 3D bioprinting or 4D printing to produce pure additive manufacturing. Here presented the preparation of 2D materials inks from 2D materials. And results of producing these printed memristors. Resistive switching characteristics demonstrate the mimics the artificial neural synapses, relaxation characteristics, current voltage characteristics present here. Also 3D schematic view of active memristor structure, 1T1R structure with flakes of WC2 transistor and printed RAM cell on the right side. I want to shortly show you our results produced in our lab. One of the technology we used, the first technology we used to produce memristive materials, this is the electrochemical technology, which have some advantages. Anodization produced at low temperature, an inexpensive and non-vacuum process that allow oxides of controlled composition and properties which can be grown on the surface of metal films of different metal elements. We use nanoscale methods for investigate the synthesize process of materials of titanium oxide and investigation of nanoscale resistive switching. Here we present the formation of oxide nanostructures of titanium dioxide, and on the right side we measure the nanoscale resistive switching stability, endurance, and present the distribution of commutative probability. We investigate the size effect of influence of thickness of titanium oxide on resistive switching processes. Here we see the dependencies of resistive switching parameters on the thickness of titanium oxide. We explain the physical mechanism. We simulate this resistive switching in dynamics. On A, we present the situation after formation of oxide nanostructure. On B, we switch the material to low resistance states. We can see formation of conductive nano bridge, and on C we present the broken of this bridge and switching the titanium oxide nanostructure in high resistive state. On the right side we modeling of chemical composition of titanium oxide nanostructure formed by anodization process and distribution of chemical composition in depth of nanostructure. We simulate the titanium of different profiles of function of anodization pulse voltages, distribution of oxygen vacancies concentration in the volume of these oxide nanostructures. We produce this simulation on MATLAB program. The next investigation, we use nanoscale current atomic force microscopy to provide the resistive switching visualization. On the figure on the left side, we can use initial high resistive state of the structure after formation. After that, we we switch the local areas on the surface by applying different voltages from 3 to 7 volts and produce current atomic force microscopy scanning and provide the visualization. On the right side, we demonstrate the different switching processes and produce the investigation of resistance retention test by current atomic force microscopy. Investigation the retention, we investigate, we produce the current atomic force microscopy after 100 days. This equivalence of 6 billion seconds. This is a structure shows good retention after this period. We produce different investigation by influence of temperature and different materials of top electrodes on memristive characteristics. Also, we simulate the physics of resistive switching in crossbar structure by using COMSOL multi-physics software. Here we can see different processes of resistive switching, process of distribution of vacancies read in the cross-sectional plate of the oxide crossbar structure. After that, we fabricate the prototype of memristive crossbar based on electrochemical titanium oxide and investigate their main properties present on this slide. This is endurance, cumulative probability, ratio of high resistive state to low resistance state, and plasticity. We investigate multi-level resistive switching, which can be used in neuromorphic structures, applications. We investigate the statistics of this crossbar layout from cell to cell for 16 different memristive structures. This is a good stability. And after that, we produce the next crossbar structure with higher miniaturization, which consists of 64 memristive structures. We investigate this structure now. For investigation of resistive switching in thin oxide films, we develop simulation model based on Python programming, which provide us investigation of influence of thickness on current voltage characteristics and on ratio, on common parameters of switching like voltages, currents, resistance. We synthesize zinc oxide films or zinc oxide by pulsed Lars deposition and investigate the main growth parameters and growth regimes. We investigate nanoscale resistive switching on these films by scanning probe microscopy, by CIFM. We present the visualization of single current bridge and current IFM of writing processes and reading processes by CIFM. Here we present the influence of different material of top electrodes on these resistive switching processes. We create cross-point mem-resistive structure and investigate them for endurance and retention test. We develop the fast prototyping method based on using scanning probe lithography, force lithography, to produce nano-sized mem-resistive structures and create these structures based on scratching probe lithography method, investigate them, and provide the statistical data, the good parameters of endurance, retention, and statistical current voltage characteristics. The main problem of investigation of crossbar structures included many mem-resistive structures. This is a long time process. For speed up this process, we develop the special hardware and software system of automatization of investigation resistive switching named NeuroInt. Here we present this device which provide us fast investigation of crossbar systems. Here presents we can connect this device to probe station, or we can connect this device to already manufactured prototype and investigate the main parameters: endurance, retention, speed of resistive switching, statistics of current voltage characteristics, and other, and convert the results in many different formats of presentation, export the experimental results. Here we present the measurement of time of resistive switching processes. This is a fast process, like 12 nanoseconds of mem-resistive structure. Here we present this crossbar structure plated in device. And then we use our memristive structure prototype to develop the neuromorphic structure of tactical memory, which can provide us feel the temperature of the water. This device was based on the finger of the robotic hand, if the temperature of water was less than 60 degrees of Celsius, the movement of head was slow. If the temperature of water was more than 60 degrees of Celsius, the reaction of the movement of fingers was very fast, like pain feeling of human's hand. That is all what I want to say about memoristic materials. Thank you for your attention. Question, please.
As usually, Professor Vladimir, it's wonderfully present, and the kind of detailing you have done for the presentation, it's marvelous.
Thank you, Dr. Lavash.
Dear colleagues, any questions? Thank you so much for your attention. Any questions?
If no questions, thank you for your attention. See you on the next section.
Dear friends, thank you very much for your interest, for your attention. We will be happy to meet you during our third pre-conference activity held by Dr. Chandra Prakash in October. So,
Sure.
bye-bye.
Sure. Thank you, everybody. Please take care.
Thank you, sir.
Thank you.
Thank you, sir. Thank you.
Thank you, sir.
Thank you. Thank you. Thank you.